Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we begin the 5th module of our course. It deals with rational numbers, the second lecture, and in particular, it's a continuation of our discussion of common fractions. It's a difficult topic, common fractions, and that's why we're doing it in two parts. Why is it difficult? What did we do last time, or what didn't we do last time that maybe we should have? Well, the problem is that to make things a little bit simpler, we rigged it a little bit. I'm reminded of the old World War II story where the sergeant came by where a bunch of men were digging, and he yelled down, "How many of you guys down there?" And the voice came back, 7. And the sergeant said, "Okay, half of you, come on up." Now, that's the kind of a problem that you really can't do. Or, well, if you could do it, you certainly wouldn't want to see the answer to that. You see, the problem with what we were doing in the past, and in fact, let's review that. We'll go over to the board in a minute. But the problem that we were stuck with in the past was that when we wanted to take a fifth of a number, for example, we always made sure that the number we were dealing with was a multiple of 5. The problem we're going to deal with today, in part, is what happens if it's not a multiple of 5. How do we handle it then? And secondly, last time in discussing common fractions, basically what we tackled was addition and subtraction. The next comparable lesson seems to be, how would you multiply and divide fractions? That will be our goal for today. So without further ado, let's go over to the board and pick up where we left off last time. And like in most good serials, we should begin with a review. The review is that the common fraction 2 over 5 is read as 2/5. You see 2 is the adjective, 5 is the noun. See numerator, enumerate, how many. Denominator, denomination, size. And when we say 2/5, it denotes the answer to a rate problem, to a division problem. 2/5 denotes the answer to the problem 2 divided by 5. And notice, by the way, that when you want to divide 2 by 5, what we did last time was that we made sure that the adjective that 2/5 was modifying, that the noun that 2/5 was modifying was a multiple of 5. Let's again review briefly. See, suppose the noun is hours. 2 hours divided by 5. Well, since there are 60 minutes to an hour, 2 hours will be 60 minutes twice, or 120 minutes. 120 divided by 5 is 24. So 124 minutes divided by 5 is 24 minutes. And notice, by the way, that since a fifth of an hour, see 60 minutes divided by 5 is 12, and 12 times 2 is 24, we see the connection between 2 hours divided by 5 and 2/5 of an hour. Now, okay, that's the review so far. Here's where the problem comes in. You see, 2/3 of 60 is fine. See, 60 divided by 3 is 20. 20 times 2 is 40. So 2/3 of 60 would be 40. But how about 2/3 of 7? You say, well, let's see. 7 divided by 3, and then we'll multiply by 2. But you see, 7 divided by 3 can't be a whole number. Why can't it be a whole number? Well, the meaning of division is what? The answer to a division problem is the number you must multiply this one by to get this one. In other words, when you say 7 divided by 3 equals blank, that's the same as saying 3 times blank equals 7. Now, let's try to solve the problem 3 times blank equals 7. It's sort of like Goldilocks and the 3 bears. We try 2, but 3 times 2 is 6, and 6 is too small. So then we tried 3, but 3 times 3 was 9, and 9 is too big. In other words, whatever number we're looking for, it has to be more than 2, but less than 3. But when you're dealing with whole numbers, there are no whole numbers between 2 and 3. And be very, very careful about that. That's one of the problems with tally marks. Somebody says, isn't this 2 1/3 tally marks? See, I'll draw 2 whole tally marks and 1/3 of another tally mark. No, this tally mark may only be 1/3 of the length of these 2, but it's still what? 3 tally marks. When I hold these 3 fingers up, there are 3 fingers there, even though one of the fingers is not the same length as the others. You see, when you're counting, you count the number of objects, not necessarily by size. If you're counting the number of people in the room, you don't say, let's see, he's kind of small, so we'll count him for 2/3. This one's pretty big, we'll count him for 1 2/3. No, you count 1, 2, 3, etc. And by the way, one of the reasons that fractions is a hard subject for people is exactly this problem of divisibility. And if you think that fractions are hard for you, notice how they were hard throughout all of history. Do you ever notice how people chose nouns to avoid fractions? We've been talking about place value in base 10, right? Counting by tens, what a nice thing it was. Let me ask you a few very simple introductory problems here. How many is a dozen? Is it 10? Or is it 12? A dozen is 12. And if 10 is such a nice number, why did they pick 12 to be in a dozen? And the answer is, when you want a third of 12, you can do that without breaking something. If you want a third of 10, that's a harder problem. You see, 12 has 2, 3, 4, and 6 as factors. You see the idea? Here's another one. What's the first teen? Teen means plus 10. So when you say 14, that means 4 plus 10. 13 is a corruption of 3 teen, 3 plus 10. Technically speaking, what should the first teen be? 11, 1 teen. But the first teen comes after 12, not after 10. Why? Because people like numbers that could break up into fractions. Remember, we dealt with an hour. How many minutes to an hour? 60. What's nice about 60? It breaks up into fractional parts without having to have so-called fractions. You can take a half of 60, a third of 60, a fourth of 60, a fifth of 60, a sixth of 60. You see the idea? The Greeks used 360 degrees to divide a circle into, because look at how many factors 360 has. If you want half a circle, it's 180 degrees. If you want a third of a circle, it's 120 degrees. If you want a fourth of a circle, it's 90 degrees. See, it has a lot of factors. But did you notice one of the problems with both 60 and 360? Sooner or later, there is going to be a number that 60 or 360 won't be a multiple of. I mean, for example, suppose you wanted 1/7 of 60. How do you divide 60 by 7? And this is where the ancient Greeks made a tremendous contribution to the history of mathematics. It's not something that we technically need in this course, but I would like to put it in for completeness. And that is, in order to deal with fractions, the ancient Greeks introduced the concept of the number line. You see, you can't take half of 7 people without causing damage, but can you take half of a piece of string that's 7 inches long? In fact, you've probably done things like this. Even without knowing the length of a piece of string, can't you divide it in half just by tying the ends together? You see, that's what the ancient Greeks did. Suppose you had a particular length. We'll call it 7 inches, but it could be any length. Suppose I wanted to divide that length from A to B into exactly 3 equal parts. Watch the technique for doing this. You see, one way of doing this is what I call the prayer method. You pick 3 points and pray that you divide it into 3 equal parts. The prayer method works better for some people than for others. The Greeks found a way that works for everybody. What they did was they drew any other line that they wanted. And on the line that they drew, they measured off 3 equal spaces. In other words, they would say, okay, I'm going to draw this line. I'm going to mark off the same distance 3 times. So they made these 3 pieces all the same length. Let's say that this ended at the point C. They then drew the straight line that joined C to B. Then through these points, they drew lines parallel to the line that joined C to B, and that divided this into 3 equal parts. So if this whole length was 7 inches, each of these parts would be what? 1/3 of 7 inches. You see, you can't have more than 2 people but less than 3 people. But you can have more than 2 inches but less than 3 inches. And that was when the idea of lengths replaced the idea of tally marks. Tally marks were simpler, but when the world became complicated enough and you had to take fractional parts of things that weren't multiples of the denominator, lengths became more convenient than tally marks. But we'll come back to that in the textbook, and it's sort of an elective topic. It's an optional topic. I just wanted this in here for completeness, and also to make the next topic perhaps make a little bit more sense. You see, so far we have discussed addition. And by the way, whenever you've discussed addition, you have indirectly discussed subtraction. In other words, once you know that 2 plus 3 is 5, you can solve the problem 2 plus blank equals 5. And that's called what? 5 take away 2, or 3. So basically, when we added fractions, we just said what? We can take a part of a number, then another part of that number, and add them together. To introduce the concept of multiplying fractions, there is a very practical thing that happens all the time. And in fact, it's quite possible that when you were in elementary school, you even heard this word being used. And that is, when you multiply using whole numbers, we usually talk about times. In other words, when you multiply 2 by 3, you usually say 2 times 3. When you multiply, for example, 2/5 by 3/7, it's usually called 2/5 of 3/7. Maybe you remember that. And the reason for that is that we will view later the operation called multiplication in terms of taking a part of a part. Do you see the psychological difference between a part plus a part and a part of a part? You see, when you take a part plus a part, you take something, then you take something else. When you take part of a part, you take something, then the part that you take part of that. So you're not taking two separate things. So let's see what happens over here. Let me give you a problem like this. Let's suppose we say, how much is 2/3 of 4/5 of 15? That may almost sound like a tongue twister, but do you see what this thing says? You're going to take 2/3 of something. 2/3 of what? 2/3 of something that's already 4/5 of 15. We'll come to a practical application of that in a few minutes. Let's just tackle this problem mechanically first. See, let's put the grouping symbols in over here. See, we're going to take what? 2/3 of 4/5 of 15. Well, what's 4/5 of 15? You may wonder, by the way, why did I pick 15 here? Well, for the same reason that we talked about in the last lecture. This tells me I'm going to be dividing by 5. This denominator tells me I'm going to be dividing by 3. To play it safe, to avoid having to have fractional parts, why not take a multiple of both 3 and 5, which is 15. So I'm taking 2/3 of 4/5 of 15. 15 divided by 5 is 3. 3 times 4 is 12. Okay? 3 times 4 is 12. Now what am I going to do? I'm taking 2/3 of the 12. 12 divided by 3 is 4. 4 times 2 is 8. In other words, to take 2/3 of 4/5 of 15, 4/5 of 15 is 12, and 2/3 of 12 is 8. So what have I done altogether? After I've taken 2/3 of 4/5, I started with 15. How many did I take? 8. So I took 8 of the 15. And look what this says. It says that at a rate of 2/3 of every 4/5, you're taking 8 out of every 15. Do you follow that okay? And look what happens over here. Look at the 8. How is the 8 related to the 2 and the 4? Isn't that the answer I would have got if I had multiplied 2 by 4? And how is the 15 related to the 3 times the 5? That's the answer I would have got if I had multiplied the 3 by the 5. So with that in mind, we say, okay, since to get the right answer, you multiply the two numerators and you multiply the two denominators, let's call this a multiplication problem. And by the way, notice this little tricky thing. When we added, we needed common denominations. When we multiply, we don't. And doesn't that check with what already happened with whole numbers? What did we say? When you have 200 times 3,000, you multiply the 2 times the 3 to get 6, and the 100 times the 1,000 to get 100,000. In the same way, when you have 2/3, see? Well, I don't know if I should, let me just write that here. 2/3 times 3/5. I want you to see how, even though this may look harder from a language point of view, it's the same thing we were doing before. See, we multiply the adjectives, so 2/3 times 4/5. Oh, this is just one of those days, okay? The 2 times the 4 gives me the 8. But remember what we said? When you multiply, you also have to multiply the denominations. The 3rds times the 5ths give me the 15ths. And just to show you how this works, let's look at one more problem. Suppose I wanted 2/3 of 4/5 of 60. Now, by the way, when might that happen? Suppose my share of something is 4/5, and there are 60 things altogether. So my share is 4/5 of the 60. Now suppose I'm only allowed to keep 2/3 of that. Suppose I have to give 1/3 to my partner. So what am I doing? I'm keeping 2/3, not of the 60, but of the 4/5 of the 60. And you see, the way this works is, again, and why did I pick 60 here again? Because 60 is still a multiple of 3 and 5. Next lecture, in Module 6, we'll get into what happens when you are forced to deal with something which isn't a multiple of 3 and 5. But look what happens over here. 60 divided by 5 is 12. 12 times 4 is 48. Now, what am I doing? I'm taking 2/3 of 48. 48 divided by 3 is 16. 16 times 2 is 32. So if I'm taking 2/3 of 4/5, I'm taking 32 out of 60. But what did we just see a minute ago? Didn't we see that that was supposed to be the same as 8/15? Just as a check, let's see what happens. Suppose I take 8/15 of 60. 60 divided by 15 is 4. 4 times 8 is 32. Same answer as we got over here. And again, whereas this looks like a fraction problem, read it as a whole number problem. What this says is, at a rate of 8 out of every 15, you will take 32 out of 60. Do you follow the idea here? And let me show you how this is used, let's say in advertising. This problem is longer than it is hard, but let me just show you the wording is actually longer than the problem itself. It says a store advertises 1/5 off the regular price. Of course, what the regular price is anybody's guess. They make up regular prices sometimes, but they say 1/5 off. And by the way, whenever somebody says 1/5 off, you ask, off what? Is it the regular price? Is it your price? Is it the list price? But basically, off suggests subtraction. And when they say 1/5 off the regular price, what they're saying is they're taking off the price $1 out of each 5. If I say to you, I'm taking off $1 for each 5 that the object costs, doesn't that sound like a whole number problem? Not a fractions problem. But anyway, let's go on. It says, if the regular price is $15, what is the sale price? In other words, at 1/5 off the regular price, what do you pay for an object that has as its regular price $15? And let me show you how you solve this problem with no knowledge of fractions at all, just dealing with whole numbers. You see, if it's $1 off, that says what? For every $5 of the regular price, you're going to save $1. They're taking $1 off that price. If they take $1 off and the regular price was $5, you're still paying $4, aren't you? Guy says, yeah, but what if the object wasn't $5? Well, let's count by multiples of 5. Suppose the regular price was $10. That's what, 2 5s? If you take $1 off of each 5, on 2 5s, you're going to be taking off $2. And if you take $2 off of 10, the sale price is going to be $8. What if the object was $15? Since you're taking off $1 for each 5, and 15 is 3 groups of 5, you're taking off $1 3 times. That means you're reducing the price by $3. 3 from 15 is 12, so you're still paying $12. And do you notice what's happening over here? The regular price could be tallied by multiples of 5. The savings are multiples of 1. And the sales price is what? Multiples of 4. Any fractions here? No, this is all whole numbers. Have I answered the problem? The problem said if the regular price is $15, what is the sale price? Well, we just found the answer. The sale price is $12, okay? Now, let me show you how the language of fractions comes in here, because this is going to be a long story to lead up to something. What are we saving? You see, at a rate of $1 out of each 5, how many are we saving on $15? Isn't this exactly what 1/5 of 15 means? In other words, if you understood what I just did, but you don't understand why I'm saying 1/5 of $15, you have a language problem, not a math problem. See, but 1/5 of $15 is $3. That's what we're saving, isn't it? If you're saving $1 out of each 5, what are you still paying? You're paying 4 out of each 5. That's 4/5. And 4/5 of the $15 is what? 15 divided by 5 is 3. 3 times 4 is 12. Doesn't that check with what we had in our chart? We're saving $3 and we're still paying $12 on a $15 item. So far, that's just a review of our previous lecture. Where does part of a pot come in? Well, what usually happens after you have a sale? Either the item moves or it doesn't move. If the item doesn't move, that's dead space. You want to turn that over. So you either give the merchandise away or you make a sale on the sale. You say, okay, we're going to reduce the price that it's already marked at for sale. So here we come to the next problem. It says a second sale, that means the same store, advertises 1/3 off the first sale price. In other words, they've knocked the price down once. Now, whatever that new price is, they're going to take 1/3 off of that. That means you're going to be paying what? 2/3 of the first sale price. Now the question says, if the regular price is $15, what is the price during the second sale? Well, look it. You already found out that during the first sale, you were paying 4/5 of $15, which was $12, right? Now you're going to take what? 2/3 of the $12. You're only paying for 2 out of every $3. That's what it means when you say 1/3 off. You're paying for 2 out of $3. So 12 divided by 3 is 4. 4 times 2 is 8. So you're paying $8. You're paying $8. $8 out of what? $8 out of 15. $8 out of 15. In other words, notice that 2/3 of 4/5 in this case is again 8/15. And by the way, let's summarize this again. See, what we said was, at $15 regular price, you take off 1/5, that's $3, you're still paying $12. Now you take off 1/3, 1/3 of 12 is 4, so you're still paying $8. Notice how this goes up by multiples, the multiples of 15, the multiples of 12, the multiples of 8. That's why we made such an issue over multiples, because you're doing whole numbers this way. You see, what we're saying is that you're paying 8 out of every $15. So if the object was priced $30, you're paying $8 twice, which is $16. If the object is charged the regular price at $45, since 45 is 3 times 15, you're paying $8 3 times, which is $24. And notice psychologically that there we're dealing with whole numbers. It doesn't become fractions until you say, hey, at a rate of 8 out of every 15, 8/15, how much will I pay on $45? And 8/15 of $45, 45 divided by 15 is 3. 3 times 8 is 24. You see, the 3 is the third multiple, and the 8 is that each time you're multiplying, you're adding on 8 more. See, this is the same problem as this. By the way, what if you changed the sale? What if this first sale had been 1/3 off, and the second sale 1/5 off? Does it make any difference whether first you take off 1/3, then take off 1/5 of what's left, or whether you do it the other way around? That's the question I'm asking over here. Is 2/3 of 4/5 the same rate as 4/5 of 2/3? And the amazing answer is, even though they may sound different, see, taking 4/5 of 2/3 is a different procedure than taking 2/3 of 4/5. The amazing thing is, how do you do an off problem? You multiply, and 4 times 2 is still 8, and 5 times 3 is still 15. In other words, whether you call it 4 times 2 or 2 times 4, the answer is still going to be 8. You see, you follow the idea there? Let's apply, in fact, let's look at it the long way first. Then we'll apply it to the sale problem. See, let's look at 4/5 of 2/3 of 15. You see what I'm doing? First, I'm taking the 2/3 of 15. Then I'm going to take 4/5 of what's left. So what I say is, okay, 15 divided by 3 is 5. 5 times 2 is 10. Now I'm going to take 4/5 of 10. 10 divided by 5 is 2. 2 times 4 is 8. I'm still taking what? 8 out of the 15. See, either way, I'm still paying what? 8 out of every $15. But look at the part that's interesting. You see, this way, the regular price was $15, so we took 1/3 off. That was $5. At $5 off, the price was $10. Then we took 1/5 off on the $10. 1/5 of 10 is 2. We take $2 off the 10. That's $8. Now let's do it the first way. We take 1/5 off of 15. 1/5 of 15 is 3. We take $3 off the 15. That leaves us with 12. Okay? Now we take 1/3 of the 12. That's 4. We subtract the 4 from the 12. That's 8. So both ways, we're paying $8. But do you notice that there is a difference, even though the answer is the same? Notice that at the end of the first sale, one way the price would be $10, the other way the price would be $12. The end result would be the same, but the process is somewhat different. And by the way, this is what's interesting. Since you're multiplying numerators and denominators to find fractional parts of fractional parts, no matter how you mix the numerators around, or how you mix the denominators around, the answers will still remain the same. For example, is 4/3 of 2/5 the same rate as 2/3 of 4/5? See how different these look? See, this one says what? Take 2/5 of something, then take 4/3 of that. 4/3 means you take what? More than what's there. You take 1/3 of it and take that 4 times. You say, how can you take 4/3? Well, for example, suppose you borrowed money and you said to the person, I'll tell you what, for every $3 you give me now, I'll give you back 4 later on. So if the person gave you $6, you give back 4 twice. That's $8. You see the idea? See, you divide by 3 and multiply by 4. But don't worry about that right now. There's plenty of drill on that in the exercise sets. What I want you to see is when you take 4/3 of 2/5, even though that sounds different from 2/3 of 4/5, how do you multiply? You multiply numerators and you multiply denominators. And the reason you do that isn't because it's easy, it's because it gives you the right answer. After all, when you were adding fractions, it would have been easier to add the numerators and add the denominators. But the reason we didn't was because we got the wrong answer. Let's just practice one more problem just for the heck of it and see how it works. This says, how much is 7/9 of 4/11? And I will work this out in more detail later. I just want to see if you know how to do this problem mechanically first. Whenever you see of, think of it as a time sign. 7 times 4 is 28. 9 times 11 is 99. So the answer to that problem is 28/99. And what does that mean? I mean, mechanically, that's an answer. What does it mean? It means if you take 4/11 of something, then you take 7/9 of what's left. It's the same as if you're taking 28 out of every 99. And I'll review that with you in a minute. The thing I wanted to show you that scares some people with fractions is when you deal with whole numbers, the word multiplication reminds you of something getting bigger. See, 3 times 2 is 6. 6 is bigger than either 2 or 3. But when I say 7/9 times 4/11, the answer is 28/99. Do you notice that the answer is smaller than either of the two factors? Remember how we compare fractions? We get a common denominator, then we compare the numerators. 7/9 is the same as 77/99. Remember that? And 4/11 is the same as 36/99. Notice that the answer is smaller than either factor. And the reason is that when you multiply fractional parts, you're taking a fractional part of a fractional part. If I take 2/7 of something, that's less than the whole thing. See, I'm taking a part of a part, okay? And let me just work that out for you just to show you how this works. You see, to see one way of what 7/9 of 4/11 is, pick a number that's divisible by both 9 and 11 because that's what you're going to be doing over here. So you say, okay, 99 is a common multiple of 9 and 11. 1/11 of 99 is 9. 9 times 4 is 36. And if I now take 7/9 of the 36, see the rate of 7 out of every 9, how many am I going to take out of 36? Well, there are 4 bundles of 9 in 36. I'm taking out 7 from each bundle. Isn't that 28 altogether? 36 divided by 9 is 4, times 7 is 28. 28 out of how many? 28 out of 99. And how do you write that? 28/99. Sometimes you can get numbers that reduce. Suppose I said to you, how much is 6/7 times 4/15? How do you multiply two common fractions? You multiply numerators and you multiply denominators. 6 times 4 is 24. 7 times 15 is 105. But now remember what I taught you last time? If the sum of the digits is divisible by 3, so are the numbers. 2 plus 4 is 6. That's divisible by 3. 105. 1 plus 5 is 6. That's divisible by 3. 24 divided by 3 is 8. 105 divided by 3 is 35. So the answer could be written in lowest terms as 8/35. How did that happen? You see, what happened over here is if we use prime factors, the 6 breaks down into 2 times 3. The 4 breaks down into 2 times 2. The 15 breaks down into 3 times 5. And so what we see is the 3 in the numerator can cancel with the 3 in the denominator. See, notice that the 3 in the denominator came from the 15. The 3 in the numerator came from the 6. But it doesn't matter because once you multiply, all the numerators are together, all the denominators are together, so a shortcut way of doing this is to cancel a 3 from the numerator to get a 2 here, and a 3 from the denominator to get a 5. Then 2 times 4 is 8, and 7 times 5 is 35. But this is a technique. This is the theory. This is how we handle multiplication. But remember what happened with whole numbers. Don't confuse how much is 2 times 3 with the problem that says, what must you multiply by 2 to get 6? See, 2 times 6 is 12. What you must multiply by 2 to get 6 is 3. That's a division problem. Let me show you how division problems come up in terms of a sale. Suppose I say, at a 1/3 off the regular price sale, you pay $60. See, that's the sale price, $60. Now I say to you, what was the regular price? Now, what is the regular price? Since it's 1/3 off, you're saving what? $1 out of every 3. That means you're still paying $2 out of every 3. So to find the sale price, 2/3 of the regular price is what? The sale price. In other words, if I take the regular price and divide it by 3, then multiply that by 2, that will give me the sale price. Now watch what happens over here. The trick here is reading comprehension. Where does the $60 go? Was the $60 the regular price or the sale price? The problem says at 1/3 off the regular price, you paid $60. That was the sale price. See, it doesn't say the regular price is $60 and you're going to get 1/3 off. See, the answer to that would be $40. This says after the 1/3 is taken off, you're still paying $60. In other words, the trick is the $60 replaces the sale price, not the regular price. So in terms of fill in the blank, remember of means times, you have 2/3 times blank equals 60. This looks like a multiplication problem, but it's really what? A division problem. And in fact, we can make this look more like a whole number problem by writing the denominator as a noun. See, write this as 2/3. Then the adjective is what? 2 times blank equals 60. If 2 times blank equals 60, okay, if 2 times blank equals 60, the blank must be 60 divided by 2. See, if twice the blank is 60, the blank itself must be 30. But the blank is only thirds, okay? How many thirds make up a whole unit? 3/3. But if 1/3 is 30, 3/3 is 3 times 30, which is 90. And by the way, don't worry about whether you understood what I said here, because I'm going to explain that in different terms later. What I want you to see is that if the sale price was 60, the regular price was 90. Does that work? 90 divided by 3 is 30. 30 times 2 is 60. See, notice that this said multiply by 2 and divide by 3. But when you put it on the other side, when the blank is over here, what did you wind up doing? Just the reverse. You divided by the 2 to turn the 60 into the 30, then you multiplied by the 3 to get the 90. Let's just look at that mechanically, and then we'll study it some more in a few minutes. See, 2/3 times blank equals 60, in terms of a division problem, says blank equals 60 divided by 2/3. But notice what we did. How do we divide by the 2/3? We divided by 2 and then multiplied by 3. You see, to divide by a fraction, we multiplied by what we got when we tipped the fraction over. That's called the inverse, and I'll explain the importance of the inverse to you in a minute. But what I want you to see over here is that, see the difference between taking 2/3 of 60 and asking the question, 2/3 of what number is 60? Okay? And let me show you another reason how you can start to visualize that to divide by a fraction, you multiply by its inverse, or it's sometimes called reciprocal. Let's suppose candy costs $6 for 3 pounds, and you want to find the cost per pound. Cost per pound, and the cost is in dollars here, dollars per pound. What does per mean? Per means divided by. So we put the 6 modifies the dollars, the 3 modifies the pounds, 6 divided by 3 is 2, and the label is going to be what? Dollars per pound. Do you follow the problem this way? See, how do we find the dollars per pound? We take the number of pounds and divide the number of dollars and divide by the number of pounds. Now let's work with a fractional number of pounds. Suppose now it's $6 for a half a pound instead of for a whole pound. See, it's $6 per half pound. What is the cost per pound? Well, since each half pound costs $6 and there are 2 half pounds to a pound, I'm going to pay $6 twice, or $12. Isn't that correct? Now, let's use the same technique that we used before. Dollars per pound means dollars divided by pounds. Okay? How many dollars did we spend? 6. How many pounds did we buy? 1/2. Therefore, what should the cost be? Reading it this way, it's 6 divided by 1/2. Reading it this way, it was what? 6 times 2. Look at these two expressions. This says that 6 times 2 is the same as 6 divided by 1/2. In other words, reading this in the reverse direction, how do you get from here to here? It says leave the 6 alone, change the division to a times, and invert the fraction. And remember, 2 over 1 means 2 divided by 1, which is 2. So these two mean the same thing, not because it's obvious, but because it gives us the answer in the real world. Let's just try a couple of more problems. First of all, I'd like you to see why we're interested in reciprocals. See, 2/3 and 3/2 are reciprocals. How much is 2/3 of 3/2? It's a real neat device. Whenever you take a number and multiply it by its reciprocal, you always get 1. Why is that? Because the numerator of this number is the denominator of this number, and vice versa. So when you multiply the two numerators, you're going to get exactly the same thing as when you multiply the two denominators. See, 2 times 3 is 6, 3 times 2 is 6. 6 over 6 means what? 6 divided by 6, and 6 divided by 6 is 1. And if you want to do this the shortcut way, you see the 2 in this numerator cancels the 2 in this denominator. The 3 in this denominator cancels with the 3 in this numerator, and you wind up with 1 times 1, which is 1, over 1 times 1, which is 1. And you say, well, isn't that nice? But what do you do with that? And the answer is, what you do with that is the following. Let's suppose I say, fill in the blank, 2/5 divided by 3/7. That means what? What number must you multiply by 3/7 to get 2/5? In other words, this is asking for the relative size of 2/5 as compared to 3/7. Now, instead of using the blank over here, because the blank looks like a fraction bar, I am just going to use parentheses. The problem says, what must I multiply by 3/7 to get 2/5? Now, watch this tricky device. The thing I want in my answer is 2/5. The thing I have in the problem is 3/7. I don't want the 3/7 in here. By the previous problem, what can I multiply 3/7 by to knock it out? Multiply it by its reciprocal. If I multiply 3/7 by 7/3, the answer is 1. And what must I multiply 1 by to get 2/5? Since any number times 1 is itself, obviously 1 times 2/5 is 2/5. So therefore, altogether, what did I multiply 3/7 by to get 2/5? I multiplied it by 2/5 times 7/3. 2 times 7 is 14. 5 times 3 is 15. Let's see if that works. If this is the right answer, 14/15 times 3/7 should give me 2/5. And look what happens. 7 goes into 14 twice. 3 goes into 15 5 times. The answer is 2 times 1, which is 2, over 5 times 1, which is 5, which is the correct answer. Now the interesting point is, compare the problem with the answer. When we divided 2/5 by 3/7, the 2/5 started off the problem. What's the first number in the answer? Isn't that also 2/5? See, we left the first number alone. What happened to the division sign? It became a times sign. What happened to the 3 over 7? It became 7 over 3. And so the answer to this problem mechanically, see, after I've shown you the answer, you can say, hey, there's an easy way to divide the first fraction by the second fraction. Namely, leave the first fraction alone, change the division sign to a times sign, and multiply by the reciprocal of the second fraction. And by the way, that works in the real world. Let me show you a real-world problem, something that you may be familiar with. It's almost like a radar trap. How do they figure out how fast you are going? They time your car over a very small distance. In other words, you don't go very far, but it doesn't take very long either. And they take the ratio of the distance to the time. See, miles divided by hours, or miles divided by seconds. And they convert that into what? miles per hour, and that's how to decide whether you're over the speed limit or not. So let me phrase a problem that way. An object travels 2/5 of a mile in, that means per, 3/7 of a minute. See, it didn't go very far, but it's 3/7 of a minute, a very long time. See, there's lots of 3/7 of a minute in a whole hour. Do you see what I'm saying here? This is a short distance, but this is also a short time. And what the problem is saying is, what is the speed in miles per minute, and what is the speed in miles per hour? Well, the trick is, everything still means the same as before. Miles per minute, per still means divided by. How many miles did the object go? It went 2/5 miles. How long did it take? 3/7 of a minute. Therefore, how many miles per minute did it go? It went 2/5 divided by 3/7. What's the mechanical recipe for dividing 2/5 by 3/7? We leave the 2/5 alone, change the division to a time sign, invert the 3/7 to get 7/3. The object went 14/15 of a mile per minute. And if that bothers you, see, watch the language again. This sounds like a fraction problem, but 14/15 of a mile per minute is the same as what? 14 miles per 15 minutes. Do you notice the psychological effect here? If I say I went 14/15 of a mile per minute, that sounds like a fraction problem. But if I say I went 14 miles in 15 minutes, that sounds like a whole number problem. By the way, how many 15-minute blocks are there in an hour? 4. So if I go 14 miles every 15 minutes, in an hour I'll go 14 miles 4 times, which is 56 miles per hour. And if you want to do the problem the other way, there are 60 minutes in an hour, so if you go 14/15 of a mile each minute, in a whole hour you're going to go 14/15 of a mile 60 times. 15 goes into 64 times. 4 times 14 is 56. So even though 2/5 of a mile in 3/7 of a minute doesn't sound like much, it's still what? 56 miles per hour. Let me give you one more problem just to show you again how this works. I want it to be clear that even though I want you to be able to do these problems mechanically, I want you, first of all, to have a feeling of what this means, and secondly, to see that all of the explanations are equivalent to using whole numbers. Let's do one more problem. I say, how much is 1/10 divided by 1/100th? What's the mechanical recipe? You divide by, you take the 1/10, change the division to a time sign, and you invert the second number. When you invert 1 over 100, that's 100 over 1. So now you have 1/10 times 100 over 1. What does that do? The 10 goes into 100 10 times. 1 times 10 is 10. 1 times 1 is 1. 10 over 1 means 10 divided by 1, which is 10. So 1/10 divided by 1/100th is 10. And this frightens a lot of people. They say, look, 1/10 is a tiny number. 1/100th is a tiny number. How in the world can you divide these two numbers and get a big number like 10 for the answer? And again, it's that relative size we were talking about in an earlier lecture. 1/10 may be small, but it's still 10 times bigger than 1/100th. See, how many hundredths does it take to make a tenth? 10 hundredths. You say, oh my gosh, I can't think of fractions that way. Well, let me just show you the adjective noun bit again. 1/10 is an adjective. Let it modify dollars. Let's take 1/10 of a dollar divided by 1/100th of a dollar. What is another name for a tenth of a dollar? A tenth of a dollar is a dime, which is 10 cents. What's 100th of a dollar? It's a penny, 1 cent. Therefore, a tenth of a dollar divided by 100th of a dollar is the same as 10 cents divided by 1 cent. What is 10 cents divided by 1 cent? 10. See, 10 cents is what? It may not be big, but it's 10 times bigger than 1 cent. You see the idea? When you look at 10 cents divided by 1 cent, you say that's an easy problem. But if I say a tenth of a dollar divided by 100th of a dollar, and you say to me, I don't understand fractions, again, you've got a language problem, not a math problem. And by the way, if a person says, gee, I think America is a great society, and you shouldn't show preference. If you're going to invert one, invert both. See, suppose a person says to me, I would like to invert both. I'll make the 1/10 into 10 over 1, and I'll make the 1 over 100 into 100 over 1. And now I'll say that 1/10 divided by 1/100th is 10 times 100, which is 1,000. And it's not that this isn't a natural thing to do, it's that this gives you the wrong answer. Division measures the relative size. Is a dime 1,000 times bigger than a penny? No. Therefore, even though you might like to invert them both, you can't do it because you get the wrong answer. And this is really important. You see, when you're just dealing with whole numbers, you don't get confused whether by mistake you wrote 2 divided by 6 rather than 6 divided by 2, because you know the answer is supposed to be 3. But when you're dealing with fractions, 2/5 divided by 3/7 doesn't sound any more or any less logical than 3/7 divided by 2/5, even though they're different problems. And let me show you this in terms of a summary. See, let's look at the 4 basic operations together. When you add 2 fractions, if you have a common denominator, keep the common denomination and add the numerators. See, 3/7 plus 2/7 is 5/7. If you're subtracting with a common denomination, keep the common denominator and subtract the numerators. See, 3/7 minus 2/7 is 1/7. If you don't have common denominators, rewrite using a common denominator and then do the problem as we did before. See, 3/7 plus 2/5. 3/7 is the same as 15/35. 2/5 is the same as 14/35. Now that we have the same denomination, we add the numerators, 15 plus 14 to get 29, and we keep the common denominator. In multiplying 2 fractions, we multiply the 2 numerators and we multiply the 2 denominators. 3/7 times 2/5 is 6/35, 6/35. In dividing 2 fractions, we are finding the relative size of the first one compared with the second one. And to get the right answer, you must leave the first one alone, change the division to a times, and invert the second. See, the 3/7 remains, division becomes a time, 2/5 becomes 5/2, and the answer is what? 15/14, which is a little bit bigger than 1. And what this says is that 3/7 may be a small number, but it's still bigger than 2/5. In fact, we just saw before, 3/7 is 15/35, and 2/5 is 14/35. See, how many times bigger is 15/35 than 14/35? It's 15/14 the size. See the same answer we got over here. But if I change the order, the 2/5 remains intact, the division becomes a time, the 3/7 becomes 7/3. Now the answer becomes 14/15, which is the reciprocal of this. You see, when you change the order, see, if one number is half of another, it means if I reverse it, the other one is twice the first. See, let me show you this in terms of an example. Suppose you spend $4 per 5 pounds. That's obviously the same as 5 pounds per $4. You see, as long as the adjective and the noun are together, do you see it doesn't make any difference which way we write this? Both of these say what? You're getting 5 pounds and you're paying $4. If you use per to mean divided by, and that means a fraction, notice the first one is $4 per 5 pounds. The second one says 5 pounds per $4. Notice that it's 4/5 of a pound, 4/5 of a dollar per pound, but 5/4 pounds per dollar. You see what happens? If I change dollars per pound into pounds per dollar, I flip the relationship. See, let me just show you how this thing works. 4/5 of a dollar. You see, a dollar is 100 cents. 100 divided by 5 is 20. 20 times 4 is 80. So 4/5 of a dollar is 80 cents. So it's 80 cents per pound. If it's 80 cents for a pound, 1/4 of a pound costs 1/4 of 80 cents, which is 20 cents. And if it's 20 cents for 1/4 of a pound, since 5/4 is 5 times 1/4, remember in a per problem, we have to multiply both numbers in the ratio by the same amount. Multiply this number by 5, multiply this number by 5, that says what? $1 for 5/4 pounds. You see, $1 per pound, $1 per 2 pounds, and 2 pounds for a dollar say the same thing. But if you leave the nouns out, one way the adjective is a half, the other way it's the reciprocal, which is 2. At any rate, this is the kind of a topic that you have to do a lot of work on. I've tried to do the best I can here to try to show you the concepts. If you're still having difficulty, read the textbook carefully, do every example. Go to the study guide, do check the main ideas, do the mastery review, do the self-test. Keep working on this until you feel you understand it. And then if you still need help, see me when you get to the self-test 5 Form B when I will go over all these problems together with you. So until that time, keep studying, have fun. Like I told you at the beginning, stay young.